All right, good morning, everyone, and welcome to our live event this morning, this Friday morning. We're going to get started in just a little bit with our guest speaker, and our guest speaker for today is Dr. Rick Fluegeman from Ball State's Department of Geology, and he's going to be talking about the geology of Mars. And this isn't a real picture of Mars here. This is actually what Mars might have looked like billions of years ago with water on the surface of it. So again, this isn't a real one, but we can see some evidence that there was once water on Mars, and Dr. Fluegeman is going to be communicating that with us. Well, I'm Dana Thompson, the director of the Brown Planetarium at Ball State University. We do have the largest planetarium in Indiana at Ball State, and we use amazing technology to help us recreate the sky. And for this online series, Your Universe, we've been exploring lots of different objects in the sky. We started at our sun, we went and explored planet Mercury, then planet Venus, and then our Earth. And now we're exploring Mars, the next planet out from the sun. And Mars is smaller than our Earth. A lot of people think it's maybe as large as the Earth or even larger, but it's about half the size. But it's still really interesting. There's so much on Mars that we can explore. And we have Dr. Fluegeman to help us with that. Because again, he's from the Department of Geology at Ball State, and he's really passionate about Mars and knows a lot about what's going on the surface and even below. So I'm going to turn it over to Dr. Fluegeman for the presentation.
Well, good morning, everybody. I'm Rick Fluegeman, and I'm a geologist, as Dana said, and I'm interested and have been interested for a long time in Mars. I've been interested since I was a kid in Mars. This was a good time to be interested. NASA started flying some very early missions like the Mariner probes past Mars. And ever since, we've been learning more and more about the planet. Now, I'm a sedimentary geologist. I study sedimentary rocks here on Earth and their fossils. But on Mars, we have a lot of sediments as well. And you look at this image on Mars, and this landscape looks like it could be somewhere in the southwestern United States. It's rather dry, kind of a reddish color. You see boulders all about. You even see some sand here with ripples made by wind action. This is showing us something about Mars. Now, there's one thing missing here, of course. Where are the plants? Even in the desert on Earth, you have plants and other evidence of life. You don't see that in any of the images on Mars. What I wanted to do this morning is to take a view of Mars from the geological standpoint, looking at it as another planet. And we're going to do that. We're going to look at a lot of the images that NASA and JPL have collected, as well as the European Space Agency, over the past decade or so. Now on Mars, what we knew about Mars for the last 200 years was pretty limited. It was still an exciting object to look at. This was an image from the Lowell Observatory taken in February 1971. So not all that long ago, at least not for me. But the planet that you can see some images. You see an ice cap up here. We didn't see any fine details of the surface, but you could see that there were light and dark regions. And it appeared that there were ice caps. And it also appeared that the ice caps grew and shrank with the seasons, or what we thought were seasons. We also had an idea that Mars was primarily volcanic in origin. And so it was considered to be primarily a volcanic planet. Now, once the Viking missions in the mid-1970s went to Mars, we learned a lot more about the planet. We know the Viking, of course, the most famous part of that might be the landers, but for geologists, some of the best information about Mars came from the Viking orbiters that were in orbit around Mars for a long time and took detailed images of the surface. With that, we found evidence of flowing water, and we could see evidence of sedimentary deposits produced by both wind and water. Now, some of this came from the landers, but we had some evidence of this from the orbiters. And a couple of things I just wanted to point out. In this image, you could see these circular features. These were identified as shield volcanoes. All right, we'll talk about what that means in a minute. And here is Valles Marineris, sometimes called the Grand Canyon of Mars. This feature, unlike the Grand Canyon on Earth, which is primarily erosion produced, produced by stream erosion and other features, this is primarily a tectonic or a fault valley, what we call a rift valley. Now, this is just a look at Olympus Mons. This image here, this is not a particular photo or a real photo, although it's created from data that was collected by the last orbiters which were around Mars. It shows this large shield volcano, and it is the largest volcano in the solar system. Now, the name shield volcano we use for volcanoes on Earth. It's considered to represent an inverted shield. This name is very old in geological usage, and probably one of the more famous shield volcanoes on Earth is Mauna Loa. This is on the Big Island of Hawaii, and in profile, it looks somewhat like Olympus Mons, but it's a lot smaller by comparison, even if you consider that the entire island of Hawaii is a part of the volcano. It's still much smaller than what we see with Olympus Mons. Shield volcanoes have a particular structure. They form over hotspots in the mantle. We call them thermal plumes, and they consist of layers of basalt lava flows. Basalt is a type of lava rich in feldspar, but it's poor in quartz. Quartz is one of the most common minerals on the surface of the Earth, but on Mars, it's relatively absent. We don't see much of it. But basalt is one of the more common materials, geologic materials at least, in the inner solar system. We see a basalt lava flow here in Iceland. We can go out in the Columbia Plateau and see layers of basalt which have built up over time. And on the moon, when you look up at the moon, you can see the dark maria, which are areas of basalt. The moon is primarily volcanic and basaltic in composition as well. But you can see basalt is one of the most common features, one of the most common materials in the inner solar system. Now, the other feature that the Viking orbiter found was Valles Marineris, and I just want to show this as well. This is a reconstructed image from the European Space Agency. This is a deep rift valley on Mars. It means it's a fault valley, all right? The boundaries of it on either side are faults, fractures in the rock on which there's been movement. Unlike the Grand Canyon, which is 1.6 kilometers deep at its deepest point, the Valles Marineris is 7 kilometers deep at its largest point. It's also more than 4,000 kilometers long, which is about the length of very large rift valleys on Earth associated with the mid-ocean ridges in the ocean basins. But the thing that I like to point out with the Valles Marineris, and one of the things that we did get information about from the Viking orbiter, although we knew that this was a fault valley and produced primarily as a rift, there is evidence of sediment and sediment transport in here. You see some features that look a little bit like deltas or alluvial fans. There are some channels, some meandering channels we see. And although the stream and flowing water wasn't really the feature that produced this canyon, it did contribute to its fill. And so we have evidence from the Viking landers and the Viking orbiters in the mid-1970s that there was some evidence of flowing water in the distant past on Mars. Now, getting back to the landers. The landers are an interesting story in and of themselves. They did some experiments about the possibility of life. That's what most people know about the Viking landers. And that's another topic unto itself. I don't want to get into that right here at this point, but you can look that up on the web as you'd like. Look up the Viking experiments and see what was going on with that and what the results were. What I wanted to point out is this image from Viking 1 lander site. We see a landscape again, not unlike the one I showed at first. This is not as high a resolution, but what we can see are dunes here. And these are dunes that apparently have been produced by wind-blown action, and we consider this to be sand based on the size of the particles. Now, sand dunes like this on Earth are made primarily of quartz sand. On Mars, there isn't much quartz. In fact, if you look at the mineralogy of Mars, we know that this is primarily basaltic. I've already said that. So that means feldspar and other minerals associated with the lava and the basalt rock itself, but it's quartz poor. And if you look at this spectroscopic map of Mars, which picks up where the quartz is present, if at all, the red, if there was red and orange and yellow, you'd see evidence of high quartz. The blue is an absence of quartz. These light areas were regions where they didn't get a return, and so this is no data up here. There's coverage on the ice cap, and at this location, the crater walls interfered with the return. But you see, what do you see here? Mostly blue, all right? There isn't much in the way of quartz on this planet. We do see evidence of quartz poor rock. We think most of that's basalt. We know it was in contact with water, which means the feldspars in the basalt will produce clays. So there's abundant clay minerals on Mars. And there's other minerals like sulfates and oxides. So this is just a general look. That sand that we saw at the Viking 1 site, it's sand size, all right, but it's not quartz. It's probably made mostly of rock fragments and maybe some sulfate minerals like gypsum. Okay, geologists like to compare to Earth. Earth is what we know. We've been doing detailed work in geology as an organized science for over 200 years. We don't know everything about the Earth, but we know a lot. And so Earth is our starting point. We want to compare Mars to the Earth. We can compare, if we look at this image of Earth, well, there's a lot of things which are obvious. Okay, the first is liquid water. It's abundant. 3/4 of the surface is liquid water. On Mars, we know there's evidence of liquid water, at least in the past, but it's sparse. If there's any there at the present, it's very restricted. Okay, so this is a relatively dry place when it comes to liquid water. Both planets have an atmosphere. Okay, the Earth's is primarily a dense atmosphere with nitrogen and oxygen, of course, we're aware of that, and other gases. But Mars is primarily a thin atmosphere. The smaller size, the gravity can't hold as dense of an atmosphere in place. There's no free oxygen to speak of in the atmosphere. And there is CO2 and some water vapor and some methane. But it's a very different atmosphere than what we have on the current Earth. And it's not nearly as dense. Both atmospheres do have clouds, though. On Earth, these clouds are water vapor, and we do have water clouds, or not water vapor, but really condensed water. But we have water clouds on Mars. A lot of that's in the form of ice clouds. But we also have clouds of carbon dioxide. The temperatures are cold enough that you get some condensation of the CO2 in the atmosphere. Again, it's CO2 ice. But it is present. We don't really see that on Earth. Okay, they're speaking of ice other than what's in the atmosphere. The Earth is unique because it has water in all three forms: gas, liquid, and solid in natural conditions. And ice is the solid water, where we have ice like we see in this image in Antarctica. It's water ice. On Mars, we have very visible ice caps in both hemispheres, and the ice is primarily water ice on Mars, but there is CO2 ice which gets incorporated into the ice caps, so there's a difference right there. Both planets have climate zones, and both do show seasonality. And the Martian year is almost double what we have on Earth, and so the seasons are lengthened, but there are distinct seasonality, which is reflected in hemispheric changes in the ice caps. The southern hemisphere ice cap grows and shrinks with the seasons, while the northern hemisphere is in opposition. It does the opposite. When the northern hemisphere ice grows, the southern hemisphere ice is shrinking. We do have that seasonality on Mars that is apparent. Both planets rotate about 24 hours. The Earth's is a little bit less than 24 hours. The Mars day is a little longer than 24 hours, but they both rotate in a very similar fashion. Both planets have volcanism. The Earth's volcanism is active at the present time. Almost every day there's volcanic activity on Earth. Mars, we aren't so sure. We know there's no obvious active volcanism, but that doesn't mean there aren't volcanoes which are still putting gas into the atmosphere. That's a possibility. There is volcanism, but they're very different between the two. Of course, Earth has life just about every place. Whether you're going deep into the Earth's crust or into extreme environments, high temperature, high acidic environments on Earth, there's very few spaces in Earth's surface or even into the shallow interior that life isn't present. This is an important part of our systems on Earth. The interaction of life with rocks and with other geologic systems. On Mars, I'm not willing to rule out life completely, but I'm going to put that as having a question mark by it. There have been some indications that Mars might have life or be biotic, but there's no definite evidence that says, and just jumps out, that says Mars has life. Now, one of the other interesting features, and to me it's one of the more prominent features of Earth, is the active plate tectonics. Now, as a geologist, yeah, you say you should look at that and see it. But this really interacts and drives most of the other features we see on Earth. This is the Earth's tectonic or deep structural system. It gives the Earth a very active existence. All right, we'll talk about plate tectonics in just a second. We have questions about whether this exists on Mars or not. Now, I wanted to just talk a little bit about plate tectonics and what it is. Plate tectonics is a theory where the Earth's crust is divided into a series of moving plates. All right, it's associated with things like active volcanism and earthquakes, but a lot of other parts of the Earth's system as well. This has been verified over 40 or 50 years of work, mostly on the deep ocean floor, but there's a lot of supporting evidence for plate tectonics on Earth. It gives rise to a very active planet. This is a view of part of the Pacific Ring of Fire. Here's Japan right here, Korea. So you're looking back at Asia. Plate tectonics, the Earth has distinct continents and ocean basins here. We have volcanism, of course. This is basaltic volcanism out here on the ocean floor, but we also have very different types of active explosive volcanism on Earth that we don't really see on Mars, or at least that we haven't seen evidence for yet. So the Earth is a very active planet. Now, you think about this, and some of the evidence we have goes back to those thermal plumes and shield volcanoes like Olympus Mons and like Hawaii. Hotspots that we talked about are in the mantle, all right? They're not in the crust. On Earth, the plates are moving. The crustal plates are moving over the hotspots. So when you look at Hawaii, the active island of Hawaii, the big island right here, this is the youngest volcanism in the Hawaiian chain. As you go off to the northwest, islands like Maui, Oahu, and Kauai, they get older as you go away from where the hotspot is in the mantle. The plates are moving over the hotspot. The volcanism appears to shift through time. Now, it's not the plume that's moving, but the crustal plate. On Mars, Olympus Mons is so large, and the other shield volcanoes we see there are so much larger than terrestrial shield volcanoes because the plates don't move. And this is some of the supporting evidence that we have to argue that Mars does not have active plate tectonics, or at least not active plate tectonics as we understand it. It may have started once. Remember, Olympus Mons is, or Bias Marinaris is a rift valley. But if it started, it stopped very early in Martian history. So whatever system we have on Mars, the tectonics, there probably are Mars quakes. There may be some active volcanism, but it isn't like the plate tectonic system we see on Earth. So this is a comparison of the geology, the overall geology of the two planets. But let's look at the surface conditions on Mars. This is another place where you can see big differences. The mean surface temperature on Mars is minus 55 Celsius. It's 218 Kelvin. All right, the average temperature on Earth is 14 Celsius, very different. The atmospheric pressure on Mars is between 6.5 and 6.9 millibars on Mars. And on Earth, that's 1,015 millibars. So Mars is a bleak place. You look at this outcrop, that looks like it could almost be Earth-like. You see some sedimentary rocks, some layered rocks here. Yeah, but this is not a place you'd want to be. Okay, it's very cold and the atmosphere is very thin. All right, this is a hostile environment. And it's just not that similar to what we see at the surface of Earth. Now, this gives rise to the question as to what about liquid water on Mars at the present time. Water, as I mentioned, has three phases. This is the solid phase on this diagram, the liquid, and the vapor phase. This is a graph showing pressure in pascals, atmospheric pressure, versus temperature in Kelvin. This is a phase diagram. You can change conditions and see how water would behave in this system. And on Earth, you could see as you increase the temperature, you'd go to liquid and then ultimately to vapor as you increase the temperature still further. On Mars, though, the conditions are a little different. I'm going to show a plot of the average Earth and Mars conditions. The blue square is the mean Earth pressure and temperature. The mean Martian temperature and pressure is shown in red. If you increase the temperature on Mars and increase the temperature this way, you don't go to liquid water. You go directly to vapor. The water ice sublimes. All right. On one of the experiments that was done by one of the Martian landers in the early 2000s, they excavated and exposed some of the permafrost, some of the soil ice to the atmosphere. And within 24 hours, it had completely evaporated without passing through a liquid phase. Think about this. People talk about terraforming Mars in the future, making it so that it's more Earth-like because it had been Earth-like in the past. We'll get to that later. But you can increase the temperature, and that does vary a little bit on Mars with the seasons. But the atmospheric pressure is always going to stay within a certain range of where it is now. And so water, liquid water, just is not stable at the surface. Unlike on Earth, we can pass from ice to liquid to vapor. And that is because of the higher atmospheric pressure. In fact, if you look for liquid water or just the presence of any water on Mars, again, the reds and the yellows are very low abundance of water. As you go up to the greens, you're increasing a little bit. The blue is even more so. Where we find most of our water is in the form of surface ice at the poles. Okay, these are the ice caps. And a lot of this, as we move away from the ice caps, is actually water in the ground. This is a gamma ray spectrometer that made this map, and it was able to get some ground penetration. And so we can detect water on Mars. We can't say that Mars is completely anhydrous or having absent water, because there is water there, but it's just not in the liquid form at the surface that we would want if we need to make the same comparisons to Earth. There is water ice, though, in places away from the poles. This is in a place called North Pole Crater, which is not really at the North Pole, but we see water ice in the shaded portion of this crater, and there's even some evidence of frost or snow on the margin of the crater. This image is enhanced just like you would do Photoshop on any image you'd take here on Earth. Most of the Mars images that are taken are brought up, increased for resolution, and they change the light so that it looks more like Earth light. In fact, that's the name of the program that they use. And So we get a better image of what is present. But these are real occurrences of water ice on the planets and on Mars. And we do see things like this, but if you increase the temperature, liquid water isn't stable. This is just going to sublime or evaporate. Oops. But there is some evidence of liquid water flow. This was an image taken of the Centauri Montes region, this crater wall right here. This was taken in August of 1999. 6 years later, this image was taken of the same place, and you see a small deposit right here. This is about 1 kilometer in length from the top to the bottom. This wasn't in that earlier image. It's thought to be some evidence of groundwater, which did make it to the surface and was incorporated in with sediment and maybe rocks. And this is more like a debris flow, but in debris flows, there is a liquid water component. It began to flow down the slope, and it shows up in this image as a brighter color because it's a little more recent, it's fresher. In exposure to the atmosphere, we can pick it out. It's thought that there may have been a small landslide up here which exposed some of the water, and in the permafrost, and the mixture with sediment preserved it or kept it from evaporating, at least for a while, so that there was some flow. Okay, this wouldn't be water flowing downhill like we see on Earth. This is very much water and sediment incorporated together. But there is some evidence of liquid flow and liquid water. We know there's water in the near subsurface in the form of ice. So that explains what this is and is likely to be. Now, I'm a sedimentary geologist. I look at sedimentary rocks and the record of them on Earth. On Mars, there are sedimentary processes. We saw dunes at the first Viking site. We know that that's something that we have. On Earth, we have a number of sedimentary processes that move sediment and deposit it in various structures and in various places. All right, it's how we get sedimentary rock to build up over time. But on Earth, our major sedimentary process is water flow. Most of the sediments we see are deposited by moving water. On Mars, we do have evidence of water flow sedimentary deposits, but our predominant sedimentary deposits that we see on Mars are deposited by wind. This is a sand dune on Mars, the Namib dune. This is a scale bar. It's 3 meters, about 10 feet. And it gives you an idea. This was taken by one of the rovers, I forget which one. But this is a sand dune. You can see some ripple marks showing up. This is a fairly large series of dunes. This was deposited by moving wind on Mars. And this is by far one of the most common active sedimentary processes that we see. On Mars, we have significant deposition, though, of sediments and sedimentary rocks in the past by groundwater. This accumulated to the movement and the accumulation of sediments at the surface. All right, this is a unique process on Mars. We do see some of this on Earth, but not very much. This is an abundant process that we see on the surface of Mars, and particularly in the geologic record. Gravity, landslides, other debris flows. This is also a significant producer of sediments and a mechanism to deposit sediments. Ice, I have a question mark. All right, on Earth, glaciers, moving ice, are significant formers of sediments and deposition agents of sediment. When we look at the area around Muncie here, it's all flat. There's sediment sitting on top of the bedrock. In some places, as much as 200 feet of sediment sit until you get to the bedrock surface. Most places, it's not that far deep. But Muncie is so flat, and northern Indiana, northern Ohio, northern Illinois are so flat because of the movement of ice and the deposition of sediment by ice. We don't have direct evidence for this on Mars. We do have ice caps in the northern and southern hemisphere, which do contract and expand on the seasons. Okay, that's not moving ice as such, that's accumulating ice. There is some suggestion in the northern hemisphere, at least, that there is some ice deposited sediment filling craters and such. So there may be some glacial movement on Mars, but that's going to take some detailed exploration to really identify that, and maybe up close observation to really verify that. But these are the major sedimentary processes that we see on Mars. And that is what I want to talk about here at the end, the geologic history and the sedimentary record of Mars. Mars has sedimentary rocks. You're looking at the Burns Formation. This is in Endurance Crater. You can see bedding here. These are sandstones, much like what we'd see on Earth. We use some of the same processes to describe rocks. We're doing it remotely. We can't go up, hit it with a hammer, and look at it with a hand lens like we would do on Earth. But we have some other tools on the rovers, spectrographs, other devices which can help us understand what the sedimentary rocks are. I don't do research directly on Mars, all right? I don't publish papers on the geology of Mars, but I'm a part of a commission that does regulate how these rocks are going to be studied. And we do look at the sedimentary record of Mars much in the way we look at the sedimentary record of Earth. We've decided we're going to classify rocks very similar way. The use of the word formation, that has a very specific meaning to geologists on Earth. It allows us to map the sedimentary rocks from place to place and to establish correlations or equivalencies from location to location. That's an important part of what we do. Another thing that we know works on Mars because it works on Earth, we don't know exactly how old the Burns Formation, these sandstones, are. But we do know by the law of superposition, which says the oldest rocks are on the bottom in any sedimentary pile or sedimentary accumulation, I can tell you that in a relative way, the rocks down at this part of the section are older than the rocks in this part of the section. These were formed first. These accumulated on top of it. It's kind of a common sense law, but it's a fundamental law of dealing with sedimentary rocks. We can do a lot of things with these rocks remotely. We can even measure a section. This is a sandstone, a group of sandstones. We know there's differences in them. We can see structures remotely. These are cross beds. You see these in a lot of places. If you've ever been to Zion National Park and look at the sandstone cliffs there, these have big cross beds. But these are sand dunes. This was probably a part of a large dune field. Some of these rocks here, this middle unit, where the rocks don't have the cross bedding, we think these were deposited by shifting water tables, all right, groundwater deposition. There are different contacts in here. We can see a lot just from a remote way. Would I like to be there looking at this in detail? Yeah, of course. But we work with what we have. These sandstones are also a little different than terrestrial sandstones. Most sandstones on Earth are made of mineral quartz and some feldspar and some other rock fragments. On Mars, we think these are produced mostly from rock fragments and probably pieces of basalt again, and there might be some gypsum fragments in there as well. These rocks are cemented, though, with sulfate minerals. On Earth, they'd be cemented with carbonates like calcite or silica. And so there are some differences that we see with the rock record, and this has to do with the geologic history of Mars. You might be able to see these black dots that seem to be distributed throughout the section. They're randomly or appear randomly distributed, no matter what type of rock they're in. Well, these are the famous blueberries from Mars. All right, and these are spherules of a mineral called hematite, which is iron oxide. They're randomly distributed, so we think that they formed after burial of the rock and that they were produced by groundwater. We do see features like this on Earth. They're not as abundant as we see on the rocks on Mars, but this is an important feature and was one of the surprises when the rovers first started taking close-up images of these rocks. Now, I've mentioned a lot about similarities between rocks like sandstones on Earth and the Martian sandstones, and there are some differences, but we can still, by analogy, reconstruct the processes. We think a lot of the sandstones were produced in a very similar way. Dunes, maybe some water flow, groundwater flow, even though that's not really common on Earth. We do see things that we can build an analog with. But there is one unique group of sediments and sedimentary rocks that we've identified on Mars remotely, and these are the dust and the dust stones. Mars is a very dusty place. In geologic history, the dust that forms has been compressed through burial into a rock type called duststone, very fine grained rock. These may form by compaction of dust and then some cementation again by sulfate minerals. There's the sulfate minerals. Okay, so it produces a rock right here that you can see is layered. And this is in the upper part of Gale Crater. That section at Gale Crater, we'll come back to that. But these rocks are somewhat like mudrocks, which include things like mudstones and shales on Earth. But they're different in a couple of important ways. They're derived from mechanical weathering. Clay minerals are derived from chemical weathering, and that's what forms shales and mudstones on Earth. But these rocks are produced by dust, iron oxide dust, that was produced from mechanical weathering. Probably with the wind, all these rocks banging into each other, and rock fragments and smaller rock fragments produce powdered material, and it's iron oxide bearing, and it produces this dust and the dust stones. All right, we've even seen dust devils on Mars, which pick up some of this dust and transport it through the atmosphere. The dust stones contain no clay. We know that from spectrography, remote analysis of the minerals. So these are rocks that we don't really see on Earth. There are some very fine-grained rocks produced by windblown dust called loess on Earth, but they're composed mostly of quartz silt and some carbonate, and they're not really analogous to what we see on Mars. So these are a unique rock type, and they do figure into the Martian geologic history. If we're going to talk about Martian geologic history, it's fine to sit there and say, I can tell you that these rocks are older than the other ones because they're below them. But we really need to have a way to put an age on the material on Mars. And the way we build timescales and that we tell time in the Martian rocks really is through crater counting. These are based on a couple of assumptions. Okay, the first is that new surfaces are uncratered. Okay, the fresher, cratering occurs, and there's evidence of abundant cratering on Mars as we see on the moon, but cratering isn't that common of an event. We get some impact, very small impact probably every day in all planets, but not anything that would make a crater, but new surfaces are uncratered. Cratering, assumption two that we use is that cratering occurs at a constant rate, at least for the last 4 billion years. So there are two assumptions that we use with crater counting. Crater counting was not developed for work on Mars, but was developed for building timescales on the moon. Before the Apollo missions went to the moon, we had a sense of the geologic history of the moon and of the different deposits. It helped them plan where to send the Apollo missions to collect data. The crater counting, where we get absolute ages on this, is the cratering rate should be similar on Mars as what we see on the moon. And we have radiometric dates on the Apollo samples from the lunar surface. And we've been able to build a timescale. And so by crater counting on Mars, we can in fact put geologic ages on many of these areas and on many of the terrains of Mars. And in fact, there is a Martian timescale. If you've ever seen the timescale on Earth, ultimately it's based on relative age dating and superposition. But we have fossils, we have a lot more data, we have a lot higher resolution on that timescale, and it serves our purposes here on Earth. The Martian timescale is different because we have to look at Mars's geologic history. And as of right now, this is what the timescale looks like. There really are only 4 recognized periods, and it is based on superposition of sediments and crater counting. And that's where these ages come from. All right, some of the names, and we'll look at what the timescale means a little later because it figures importantly in the history of water on Mars. And we can see the geologic history exposed at Gale Crater, and this is probably one of the most important sections that was imaged on Mars. Okay, this is a JPL image. You can look this one up yourself. You can see bedded rocks up here at the top. As you go down, there actually is bedding down here, but the bedding is at a different angle. This is a feature on Earth we see that we call an unconformity. When the geologists working on this section, they first put a name on this. They said this is like the Grand Canyon section in Mars, but of Mars. And there is some similarity, I guess. But because it has a long geologic history presented here, we can look at this and identify different characteristics of the rock. Again, the rover has made its way up to the base of the section, but there's been significant spectroscopy, and they've recognized what these units are, these sedimentary rocks are, and have correlated into this section. So they have a pretty good idea as to what's here. And in fact, we can do a measured section again. This is meters along the surface here, and the rover was able to get an idea of elevation above the base of the section and identify the different types of rocks. For example, at the base, they recognize that this is a clay-rich section, and it represents a very different geologic history than what we see up in the middle part of the section, where the rocks are sulfate-bearing. These are like the Burns Formation, and they have sulfate-bearing sediments up in here, sedimentary rocks. And this goes up, there's a gap in the section. They just weren't able to put this all on the image on the slide. But if you go up to the top of the section, this is where the dust stones, that image I showed you from Gale Crater, these are up at the top. There is an unconformity, a gap in the record, a real gap in the record before those dust stones are deposited. And this is a real slice of the geologic history of Mars. Okay, we're able to associate this with the various time periods, and we can go back to that time scale and recognize that the material that had abundant clay represents a period where there was abundant liquid water on Mars. And the pH was near neutral. We think the Earth, the temperature may have been similar to what we see on Earth. pH near neutral, it means that it's not really acidic or basic. It's similar to what we see on Earth natural waters today, which are slightly acidic. We do see evidence in the rocks, though, of decreasing time or decreasing temperature through time. And we think the temperature began to decrease. We think at this point, at about 3.7 billion years or 3,700 million years before the present, we think that the conditions began to change and that we had decreasing liquid water and the pH began to decline. It got more acidic. As we go through geologic time, after about the 3 billion year point, Mars was very different than the Earth. And we think this was anhydrous, that most of the liquid water had been removed. This is based on what we can see in the rocks. This isn't just a guess. All right, this is based on the data that's in the rocks. As we learn more about the rocks and the sedimentary record on Mars, we'll be changing our ideas about the evolution of Mars. But based on the data that we have, this is our model for the evolution of Mars. that early atmosphere was probably comparable to Earth's, at least in density. The primitive Earth atmosphere before 2.5 billion years had little free oxygen. We think that was the case on Mars. It was dominated by carbon dioxide and water. Okay, this drives a greenhouse effect on Mars, and it would have kept the temperature probably above 0 degrees Celsius on average. And at the surface, that's important because you can have liquid water. And if you have a dense atmosphere similar to Earth's, so if you have atmospheric pressure similar to what you have, you can have liquid water at the surface. And we have some evidence of that when we look at things like stream channels and those deltas I pointed out way early on. So if we look at the history of Mars, the abundance of water, the size of the planet, we think there was probably an ocean on Mars, developed about 4 billion years ago, probably the same time the oceans developed on Earth. They're a bit smaller in distribution than what we see on Earth. On Earth, oceans cover 3/4 of the Earth's surface at the present time. On Mars, at its maximum, it probably only covered 1/3 of the planet. Average depth, based on the elevations of these basins that we see, are probably only 1,700 meters. The average ocean depth on Earth is 3,729 meters. And there are a lot deeper places on Earth and fairly shallow ones too. But the point is, on Mars, even with its lesser gravity and its smaller size and its lack of plate tectonics, very well could have had an ocean. And when we look at the record of Mars, there is some evidence from remote images, from orbital images, of what appears to be a shoreline. If you look, there's no craters out on this plain out here where this is a sediment covered plain. No craters, it's a relatively young feature. All right, we see some other terrain. This is going toward Olympus Mons. This square you're looking at, this is where it's located on the surface of Mars. Here's Olympus Mons. Some of these features are associated with the volcano itself. Lava flows, and these are some erosional features making their way toward the shoreline. But there does seem to be some evidence of a geographic feature that could have been an ocean basin. This is speculative, all right? There are other interpretations of that ridge. But geologists are beginning to think that there should have been an ocean and likely was an ocean on Mars. But the question is where did it go? About 3 billion years ago, volcanism rapidly decreased. Why? Because there's no active plate tectonics on Mars. Mars was cooling down. The internal heat of the Earth drives an active plate tectonics. All right, on Mars, that wasn't happening. Now, as you would expect, CO2 gets dissolved into the ocean. That happens on Earth as well, but there's no replenishing source of CO2 on Mars. All right, so atmospheric pressure with the lesser gravity, the planet wasn't able to hold a dense atmosphere, and CO2 began to dissolve into seawater on Mars. You increase the acidity of the water, of course, but you also reduce the greenhouse effect. Mars begins to cool down. And so what happens? Atmospheric pressure drops, the water begins to boil off and evaporate into the atmosphere, and then escape the planet altogether. It still holds an atmosphere, but not like what we see on Earth. Now, all of these things assumes that Mars had no life, that it was abiotic. We know on Earth that the biosphere, the organisms, they are important in interacting with the atmosphere. They interact with the hydrologic system. They interact with the geologic system. But on Mars, we have no evidence that no direct evidence that there was life. And so that might change our model of this. But I do want to end today and just leave you with a question. Since there was an ocean, can a planet remain abiotic or have no life if you've got liquid water and all the conditions that implies, So significant atmospheric pressure, temperatures above freezing. So you had liquid water at the surface. And active volcanism. Active volcanism produces silicate rocks, and which, when they weather in contact with water, they produce clays. Clays are very important, we think, in the origin of life. So if you put those together, can Mars have been abiotic throughout that? Can you have a liquid ocean and not have life? On Earth, we know that some of the oldest rocks we have, about 4.2 billion years old, have structures produced by blue-green algae. These are called stromatolites. And blue-green algae produce those. So in the very oldest rocks we have on Earth, there's evidence of life. So life was a very early feature on Earth, once you had liquid water and once you had volcanism. We know the conditions on Earth and Mars were very similar at about 4 billion years before the present. But at about 3 billion years, their evolution, their planetary evolution, began to take a different path. And so that's where I want to leave it, and just for everybody to think about that. So, all right.
Thank you so
Thanks
much
for listening.
Thank you so much, Dr. Fluegeman. So I actually have a question, and that is, if you could go to Mars, would you, to explore some of these things up close? Because we have rovers, we have landers, we have orbiters,
Right.
but we don't necessarily know everything about the surface of Mars because we can't go there and explore it up close. We've never sent humans there. So would you want to go?
30 years ago, I would have said yes. I think the evidence for life on Mars is beginning to increase. And so we have to consider what we can learn by doing direct observation on Mars, and whether we want to destroy an ecosystem that is, or potentially destroy it, that may be surviving from the early stages. I mean, it's pretty clear that we're not seeing forests and large areas of plant life and animal life on Mars right now. If there is life on Mars, and I think there's evidence in some form that there is, I think it's going to be extreme life, like we see extremophiles living in hot springs here. Do we want, as careful as we can be, do we want to risk contaminating the Martian surface? That's a question that we have to ask, and it's not really just a question for scientists to ask, really. There's also the issue of the expense and what we can learn, but as good as the rovers are, as I look at this, I can see things that I would like to do at Gale Crater, for example, or with the Burns Formation. I can see things that we just can't do from a rover. Now, I don't have the spectrograph on me, but they can do things that a geologist can't do, at least not just as a standard field geologist. But I think that's a serious question, and not only for Mars, but with any exploration we would do for the water planets like Enceladus or Europa. Do we want to be poking around in there?
Yeah, the water moons, yeah.
Yeah, if Mars could be verified as abiotic, I think exploration is reasonable. And I would go if I were younger, probably. They wouldn't let me go now, probably, but.
Yeah, well, we do have, NASA does have the Mars 2020 mission planned to launch in July. And that rover is named Perseverance. And Perseverance is going to maybe pave the way for future human missions. NASA's maybe planning to do that not until 2030. But there is that really important question, the ethics question of, should we be contaminating these worlds, especially if they might be able to harbor life? And that is a topic that I would like to get some experts for maybe a panel for another event, because it is a really important question, as you mentioned. And like you said, it's not just a question for geologists or astronomers, but for even philosophers and so on.
But you also have to look at returns, just the scientific information you can gain. um, by going there. Whatever you do, if you send a mission to Mars, I assume people will want to come back. And so you're going to be limited on the surface of Mars. And what can you do as a human observer that will contribute to our scientific knowledge of Mars overall? And you really have to look at the goals of the scientific investigation of Mars as well. An example from a long time ago, actually about the time Viking was conceived, the Apollo mission, the missions to the moon, there was a plan to use some of the Apollo craft to do flybys of Venus. At the time, we had no information. And it was within the technology of the Apollo equipment in the 1970s to do that flyby. Venus is a lot closer than Mars, and I'm surprised NASA isn't looking at that as a way to test the equipment. It's just something they're not doing. Scientifically now, the Magellan probes added so much to our knowledge of Venus, there really isn't much reason to send humans into orbit around Venus. But it was something we could have done, but we didn't. We're not any worse for that, except just bragging rights, I suppose. But it is something, the science of Mars, there are groups of people. I don't consider myself one of the people who's one of the Mars researchers, although I do research the topic. This is, as I said earlier, this is one of my hobbies, one of my passions in science. And I've been interested in it since I was a kid. And there's data that is available to anyone. If you want to look at the JPL images, you can look at them. You can study them. But this is something, if we're going to send a mission to Mars, you have to consider the cost, and the cost not only in money, but the cost to potentially changing an environment. We don't know if there's an ecosystem on Mars. I think there's some provocative evidence that there is something there, and mostly I get that from the presence of methane in the atmosphere, and the fact that it is being replenished.
Methane is definitely a topic of interest, and it is a topic of interest in general, just if there's life and people want to know. So Colin Combs is saying, thank you so much for your presentation, and that maybe there could be a BSU or Ball State group field trip to Mars in 2030. But then also Jean Mayer wants to know, microscopically, what do you think would be seen in Mars's water compared to Earth water? So some of the evidence that we've seen and why there can be liquid water on Mars is because it's very salty. But do you know anything more about that water?
The water is probably acidic, or low pH, I'll say that. When I say acidic, people think of sulfuric acid or something. It's not like that, but I think it's likely to have a low pH. The dissolved salts are probably sulfates, all right? But, and people forget that seawater itself, and salinity is a measure of dissolved salts, not just sodium chloride. You can taste that. But in seawater, there's a significant amount of dissolved sulfate as well. I think the groundwater is going to be saturated with sulfates. I don't know what that groundwater near the pole would be, if it's going to likely be fresher than what we see in the ice caps. I think that would be an interesting way to examine the water on Mars, is to look at just how that ice in the ice cap forms. Even on Earth, where you get the ice caps, and this is mostly what we're looking at on Mars, I think, is more analogous to the Greenland and the Antarctic ice sheets, although we don't think these are glaciers there, but it's likely snow, falling as snow rather than sea ice. There are pockets of liquid water. If it's falling as snow, or if it's atmospheric water, that water's probably fresh up there. And I don't know what happens as it sits there on the surface. You're not going to evaporate salt into the atmosphere. And that, I think that's going to be interesting when we start looking at the salinity and the chemistry of that groundwater. That's extremophiles on Earth do live in highly salty waters. They're halophiles, they call them, and there are bacteria which live in these extreme salt environments. So I think that's something we could be looking for. And I'm not. This is another part of that question about going to Mars. If it is biotic, we're going through a pandemic now. I really don't want to bring Mars rocks back inside the atmosphere. All right. They can study them on the moon. If they're going to build a lunar base, they can study them up there. I don't think we need to be bringing microorganisms that we've never come into contact with back into the Earth atmosphere.
Yeah,
but that might be in the groundwater.
Yeah, that's a great point. So we have a lot of people thanking you for such a wonderful lecture, and we really appreciate you taking your time today to be a guest for your Universe series. We have some Ball State faculty and staff who are watching, it seems, and including Art Hill and Spencer Davis, who are saying that you really know your stuff. So that's wonderful to see. So unfortunately,
well, thanks,
we are out of time. Yeah, thank you so much for everyone for watching. But unfortunately, we are out of time. So I want to just let everyone know that we are going to be having another live event next Friday, May 29th at 11 a.m. And that is all about asteroids. So we've been exploring different astronomical objects. We are not just doing planets. We are also going to explore the asteroid belt, which is mostly between Mars and Jupiter. So before we head off to our next planet in the series, we're going to stop and check out some asteroids. So we hope that you join us then. Thanks so much for watching, everyone. Have a great rest of your day. And if you have any other questions and you're watching this later, stick them in the chat and we'll get them answered. Take care, everyone.